All right, so we're diving into ceramics today.
Okay.
You know, I've been listening to these lectures you shared with me, all in Portuguese. And I
Yeah.
gotta be honest, when you first said ceramics,
Yeah.
my brain went straight to like pottery and those colorful rooster figurines you see
Yeah.
everywhere in Portugal.
The Gullo de Barcelos.
Yeah.
A classic.
Right.
Yeah, it's easy to think of ceramics as just being decorative,
Uh-huh.
but there's so much more than that.
Okay.
In fact, you might be surprised to know that, like, the Earth itself is largely a ceramic.
Whoa.
Yeah.
Hold on. Are you saying our planet is basically one giant piece of pottery?
Not pottery,
Okay.
but the Earth's crust is primarily composed of oxides,
Okay.
like silicon dioxide,
Okay.
which is basically sand or quartz.
Okay.
And guess what? Those are the building blocks of most ceramics.
So we're literally living on a giant ceramic ball.
Pretty much.
Wow, that's humbling. Okay, so if ceramics are everywhere,
Right.
why do we usually just think of like dishes and potions?
There's a whole other hidden world of ceramics beyond the traditional stuff. The lectures you shared actually break it down into two main categories.
Okay.
Traditional ceramics,
Okay.
which are what most people are familiar with.
Right.
And then you've got technical ceramics.
Okay, so traditional, we're talking about like
Yeah.
the clay pots and tiles, things that we've been using for centuries.
Yeah.
What makes technical ceramics different?
Think of technical ceramics like the high-performance athletes of the ceramic world.
Okay.
They are engineered for very specific, demanding jobs.
Okay.
Instead of using a mix of natural materials like clay, they're often made from pure compounds,
Okay.
like aluminum oxide,
Okay.
which is used to make things like spark plugs, or silicon carbide,
Okay.
which is incredibly hard
Right.
and is used for things like high-performance brakes.
So it's like comparing a hand-built clay mug to a super strong, like, engine part.
Exactly.
They're both ceramics, but on completely different levels.
Yeah, and because they're made with such precise compositions, technical ceramics have some really amazing properties.
Okay.
They can withstand extreme temperatures.
Okay.
They're super hard.
Right.
And they're incredibly resistant to wear and tear.
I see why these lectures dive so deep into, like, the atomic structure of ceramics. Then it's not just about what they're made of.
Right.
It's how those tiny building blocks are arranged.
You got it.
Okay.
The way those atoms are bonded and arranged determines everything about a ceramic's properties.
Okay.
From how strong it is
Right.
to how it behaves at different temperatures. The lectures you shared actually go into detail about ionic and covalent bonds,
Okay.
which are the two main types of bonds that hold ceramic atoms together.
I remember learning about those in school, but honestly, it was a little bit of a blur. Can you refresh my memory a little on what makes these bonds so special?
Sure.
Okay.
Imagine ionic bonds
Okay.
as two atoms clinging to each other like magnets with opposite charges.
Okay.
One atom gives up an electron, the other one takes it.
Sure.
And boom, they're locked in a tight embrace.
Okay.
Covalent bonds, on the other hand, are more like two atoms holding hands and sharing electrons.
Okay.
It's like a teamwork situation where they pool their resources to become more stable.
Okay, so ionic bonds are like super strong magnets.
Yeah.
And covalent bonds are more like a tight-knit team.
Pretty much.
Got it.
Yeah.
But why should I care about these like tiny atomic bonds? You know? Do they really affect like how a ceramic behaves in the real world?
They absolutely do.
Okay.
Those strong ionic and covalent bonds are the reason why ceramics can withstand incredibly high temperatures without melting. It's like trying to break apart two powerful magnets,
Yeah.
It takes a lot of energy to pull them apart, right? That's why you can stick a ceramic dish in a hot oven and not worry about it turning into a gooey mess.
So that's the secret behind those like heat-resistant tiles
Exactly.
they use on spacecraft and things like that.
Yeah.
I guess those tiny bonds are holding strong.
They are.
Even when things are literally heating up around them.
Exactly.
That's cool.
Yeah.
So it's not just heat.
Right.
Those strong bonds also make ceramics incredibly hard and resistant to like wear and tear.
Right.
You think about a diamond.
Yeah.
It's essentially a giant crystal made of carbon atoms held together by super strong covalent bonds. And that's why it's one of the hardest materials on Earth.
Exactly.
Wow.
Uh-huh.
Okay, I'm starting to see how understanding like these atomic bonds unlocks a whole new level of appreciation for ceramics.
Definitely.
But the lectures also mentioned something about different ways that those atoms can be arranged.
Yeah.
Is that right?
You're remembering correctly.
Okay.
There are two main ways atoms arrange themselves in ceramics.
Okay.
You have crystalline structures.
Okay.
And amorphous structures.
All right, so crystalline.
Think of a crystalline structure like a perfectly organized marching band.
Okay.
All the atoms are lined up in a precise repeating pattern, giving the material incredible strength and stability.
So a diamond is like a perfectly synchronized marching band.
Yes.
All those carbon atoms in perfect formation.
Right.
Makes sense. What about the other type, amorphous?
Amorphous structures are more like a mosh pit at a concert.
Okay.
The atoms are all jumbled up. There's no real order or pattern.
Okay.
Glass is a perfect example of an amorphous ceramic. Even though it's hard and it can withstand heat,
right,
it doesn't have that same level of organized structure as a diamond.
Okay, so crystalline is all about order and precision.
Yes.
While amorphous is more free-flowing and chaotic.
Exactly.
But how does this, difference in arrangement actually play out in the real world?
Well, it affects everything from how a ceramic breaks to how it's made.
Hmm.
Crystalline ceramics, with their tightly packed atoms, tend to be very strong.
Okay.
But they can also be brittle, meaning they can shatter if they experience, sudden impacts.
Okay.
Think of, a delicate porcelain teacup.
So that's why my favorite mug survived a drop on the counter, but shattered into a million pieces when I dropped it on the tile floor.
Right.
That makes sense.
Yeah, that sudden impact was too much for that organized structure to handle.
Right.
Amorphous ceramics, on the other hand, tend to be a bit more forgiving. They might crack or chip, but they're less likely to completely shatter because their atoms aren't as tightly bound in a specific pattern.
That makes sense.
Yeah.
So knowing whether a ceramic is crystalline or amorphous can help us understand how it might behave under stress.
Exactly.
And speaking of stress, the lectures also mentioned something about a glass transition temperature.
Okay.
Now, that one sounded a bit complicated.
It's actually not as complex as it sounds. The glass transition temperature
Yeah.
is basically the point where a molten material, like melted silica, cools down and transforms from a liquid into a solid, what we know as glass. It's the temperature where those jumbled up atoms in the liquid suddenly freeze in place.
So it's like a dance party where everyone suddenly freezes mid-move when the music stops?
Exactly.
That's a good way to visualize it.
Yeah.
But why is this glass transition temperature so important?
It's crucial for understanding how to make glass and how to control its properties. By controlling the cooling rate, you can influence how those atoms freeze in place.
Right.
And ultimately determine the final properties of the glass.
So slower cooling might create a denser, stronger glass, while faster cooling could result in a more brittle, delicate glass.
You're on the right track.
Okay.
The cooling process plays a huge role in shaping those final characteristics of the glass.
Okay.
And here's where things get really interesting. The lectures suggest that theoretically, any oxide could potentially be made into a glass.
Okay.
With the right cooling process.
Wait, hold on.
Yeah.
Are you saying we could potentially have glass made from,
potentially,
metal?
Yeah.
Or even something like wood?
It might sound crazy, but that's the idea that these lectures are presenting.
Okay.
It all comes down to manipulating those atomic bonds and that cooling process to achieve the structure and properties that you want.
Wow.
Imagine the possibilities.
Okay.
Glass skyscrapers, glass furniture made from exotic materials.
My mind is officially blown.
Yeah.
I never thought I'd be this excited about the possibilities of glass.
Right.
But before we get lost in a world of futuristic glass creations, let's get back to, the basics of how these amazing ceramics are actually made.
Okay.
From what I gathered from the lectures, it's not just about a potter's wheel, right?
You're absolutely right.
Okay.
The world of ceramic manufacturing is incredibly diverse. There are traditional methods, like hand-building techniques that have been used for centuries. And then there are high-tech industrial processes that can churn out thousands of ceramic parts in a matter of hours.
Wow. All right. I'm ready to get my hands dirty.
Okay.
Figuratively speaking, of course.
Yeah.
Walk me through some of the techniques that these lectures highlight.
Sure.
What are the key processes involved in turning raw materials into those incredible ceramic objects we see all around us?
All right. So let's start with those traditional methods.
Okay.
The ones that have been used for centuries to create everything from simple pottery to intricate sculptures.
Okay.
These techniques often involve shaping clay by hand, using tools like pottery wheels,
right?
molds, sculpting knives.
It's amazing to think that people have been using these same basic techniques for thousands of years
I know.
to create such a wide range of objects.
Right.
What's like the key to making these traditional methods work?
It all comes down to understanding the properties of clay.
Okay.
And how to manipulate it.
Okay.
Clay is this amazing material that's incredibly malleable when it's wet,
right,
but then becomes hard and durable when it's fired.
So it's like a sculptor's dream. You can mold and shape it while it's wet.
Exactly.
And then it basically solidifies into a permanent form when you fire it.
Exactly.
That's really cool.
And the firing process is what really transforms the clay from a soft, pliable material into a hard ceramic object.
Right.
The heat of the kiln causes those clay particles to fuse together, creating that strong, solid structure.
So the kiln is like this magical oven that turns simple clay into like this durable ceramic.
It is.
That's pretty cool.
Yeah.
But what about those like high-tech industrial methods you mentioned?
Right.
How do those work?
Industrial ceramic production is all about efficiency and precision.
Okay.
Instead of hand-shaping clay. These processes use highly controlled methods to create ceramic parts with very specific shapes and properties.
Okay, so it's less about artistry and more about engineering at that point.
Precisely.
Okay.
One common industrial technique is called pressing, where ceramic powder is compacted into a mold under high pressure. This creates dense, uniform objects like tiles or bricks.
It sounds a bit like making like a giant ceramic cookie.
Yeah.
You press the powder together and boom, you've got a solid shape.
That's a good analogy.
Okay.
Another technique is called slip casting,
Okay.
which is used to create more complex shapes
Okay.
with thinner walls. It involves pouring a liquid mixture of ceramic particles called slip
Okay.
into a mold
Right.
and letting that liquid absorb into the mold,
Okay.
leaving behind a solid shape.
So it's like a reverse molding process where the liquid forms the object instead of filling the space around it.
Right.
Pretty clever.
And then there's extrusion, which is kind of like squeezing toothpaste out of a tube.
Okay.
A ceramic paste is forced through a die,
Right.
creating long, continuous shapes,
Got it.
like pipes or rods.
Okay, so we've got pressing for like those sturdy uniform objects, slip casting for those more intricate, thin-walled shapes, and extrusion for creating long, continuous forms.
You got it.
It's like a ceramic toolbox with the right tools for every job.
Exactly.
That's awesome.
And no matter which method you use, the final step is crucial.
Okay.
Bonding those ceramic particles together to create that strong, solid object.
Right.
For traditional ceramics, it's firing in a kiln.
Yeah.
For technical ceramics, it's a process called sintering,
Okay.
which involves heating the ceramic to a very high temperature,
Okay.
but below its melting point.
So both firing and sintering are about using heat to solidify the ceramic,
Right.
but they work in slightly different ways.
Yes, in firing, the heat actually melts some of the materials in the ceramic, creating a glassy bond that holds everything together. Think of it like melting cheese on a pizza.
Oh, right.
It binds all the toppings together.
So firing is like adding the cheese to the ceramic pizza.
Exactly.
What about sintering?
Sintering is a bit different.
Okay.
Instead of melting,
Yeah.
the high heat causes the atoms in the ceramic particles to diffuse and move around,
Okay.
creating strong bonds that solidify the material.
Mm.
It's like those atoms are holding hands and forming a tightly knit network.
So sintering is like creating this strong web of interconnected atoms throughout the ceramic.
Pretty much.
Okay.
Yeah.
And that brings us to like the one challenge that seems to come up again and again with ceramics.
Yeah.
Their brittleness.
Ah, yes, the Achilles heel of ceramics.
Right.
We've talked about how strong they are, especially under compression.
Yeah.
But they're also notoriously prone to shattering.
Yeah.
Particularly under tension.
Right.
It's the trade-off
Right.
for those incredibly strong atomic bonds.
Right. Those bonds make ceramics incredibly strong,
Yeah.
but also somewhat unforgiving when it comes to like impacts or bending.
Exactly.
Uh.
Even a tiny flaw or defect in the material can act as a stress concentrator,
Okay.
causing the ceramic to crack or shatter under tension.
Hmm.
Think of it like a chain.
Yeah.
It's only as strong as its weakest link.
So a tiny crack in a ceramic is like a weak link in a chain.
Exactly.
It's the point where the whole thing can break under pressure?
Precisely.
Yeah.
And unfortunately, those tiny flaws are almost impossible to completely eliminate.
Right.
Especially in traditional ceramics made from natural materials.
Okay.
But the good news is that material scientists and engineers have come up with some pretty clever ways to make ceramics tougher and more resistant to those catastrophic failures.
Okay, now you've got my attention.
All right.
What kind of tricks do they have up their sleeves to overcome this, like, brittleness problem?
Well, one approach is to just be super meticulous during the production process, minimizing the formation of those pesky flaws and defects.
Right.
This involves carefully selecting raw materials, controlling the processing parameters with incredible precision, and implementing rigorous quality control measures.
So it's like saying, let's build this ceramic with the utmost care and attention to detail.
Exactly.
Making sure there are no weak points.
Precisely.
Okay.
But even with the most meticulous production methods, some flaws are inevitable.
Right.
That's where reinforcements come in.
Okay.
It's kind of like adding steel rebar to concrete to make it stronger.
Okay, so you're basically adding a support system within the ceramic.
Exactly.
To help it withstand those stresses.
Precisely.
Okay.
These reinforcements can take the form of fibers, whiskers, or particles that are dispersed throughout the ceramic material. They act like little roadblocks to crack propagation, preventing those cracks from spreading rapidly through the material.
So it's like setting up a series of checkpoints within the ceramic.
Exactly.
To stop those cracks in their tracks.
You got it.
That's pretty clever.
And then there's one of the most fascinating and effective techniques for toughening ceramics. Transformation toughening. This method relies on the ability of some ceramic materials, like zirconia, to exist in different crystal structures. Depending on the temperature and pressure.
Okay, this sounds a bit complicated. Can you break it down for me a little?
Imagine zirconia as a quick change artist that can switch between different costumes, depending on the situation.
Got it.
At room temperature, it prefers to wear a costume called the monoclinic phase. But with a little persuasion, we can convince it to wear a tougher, more resilient costume called the tetragonal phase.
So we're basically forcing the zirconia to, like, adopt a more robust persona.
Exactly.
How do I do that?
We add a bit of magic dust in the form of a stabilizer. Like yttria. This stabilizer helps the zirconia stay in its tough tetragonal phase, even at room temperature.
So the yttria is like a fashion stylist.
Yes.
Helping the zirconia maintain its, like, tough guy look.
Exactly. Now here's where things get really interesting.
All right.
When a crack starts to propagate through the ceramic, the stress at the crack tip triggers a transformation in the zirconia. It suddenly switches from its tough tetragonal costume back to its more relaxed monoclinic costume.
So the zirconia is like, hold on, crack. I'm not going to let you ruin my tough guy image.
Precisely. But here's the kicker. The monoclinic costume takes up slightly more space than the tetragonal costume. So when the zirconia transforms at the crack tip, it expands slightly, pushing against the surrounding material.
Well, it's like the zirconia is flexing its muscles at the crack tip, saying, back off, crack. I'm not going down without a fight.
Precisely this expansion creates a compressive stress zone around the crack tip, effectively squeezing the crack shut and preventing it from spreading further.
That is seriously impressive.
It's a cool technique.
It's like turning the zirconia's weakness into a strength. Using its ability to transform to actually stop cracks in their tracks.
Exactly.
That's so cool. So thanks to these techniques, we've got ceramics that are not only strong, but also tough enough to withstand those, like, everyday bumps and shocks. Where do we actually see these toughened ceramics in action? So we've talked about how those tiny atoms arrange themselves, how we can manipulate them to make different types of ceramics, and even some clever tricks to toughen them up. Now I'm ready for the grand finale. Where do we actually see ceramics in action? I mean, I know they're in obvious things like dishes and tiles, but where else do they pop up?
That's the exciting part. Ceramics are so versatile that they're hiding in plain sight all around us. We've already touched on some applications. But the lectures you shared really dive into how essential ceramics are in both everyday objects and cutting-edge technology.
So we've got the classics. Bricks, Tiles, pottery.
Right.
What else? What are some examples that might surprise me?
Well, think about your morning routine.
Okay.
You might use a ceramic mug for your coffee.
Right.
But did you know that the heating element in your toaster is also likely made of ceramic?
Wow, I never really thought about that.
Yeah.
It makes sense, though, considering those high temperatures.
Exactly. Ceramics can withstand those extreme conditions.
Right.
Without breaking down or melting.
Yeah.
And then there's your bathroom.
Okay.
The sink, the toilet.
Uh-huh.
Even those sleek, modern faucets
are
often made with ceramic components.
So ceramics are literally all around us.
Right.
From the moment we wake up to the moment we
use the bathroom.
Exactly.
Right.
And it's not just in our homes.
Okay.
When you head out for the day,
Yeah.
think about the spark plugs in your car's engine. Those tiny but crucial components that ignite the fuel and get you moving.
Right.
They have to withstand incredibly high temperatures and pressures.
Right.
Which is why they're often made of a tough, technical ceramic.
So every time I turn the key, I'm relying on the power of ceramics to get me going.
You are.
That's pretty cool.
And if you think about industries like aerospace or medicine, the use of ceramics becomes even more impressive.
Okay.
Those heat-resistant tiles that protect spacecraft during re-entry into Earth's atmosphere.
Right.
Those are ceramics.
Wow.
And the artificial hip joints and dental implants that help people regain mobility and confidence.
Yeah.
Many of those are also made with advanced ceramic materials.
So ceramics are helping us explore space.
They are.
And even heal our bodies.
Yeah.
That's mind-blowing. I know. It's a testament to how versatile and adaptable these materials are.
Right.
And with all the research and development happening in the field of material science, the future of ceramics look even more promising.
You mentioned earlier that theoretically any oxide could be made into a glass with the right cooling process. That opens up a whole world of possibilities.
It does.
What are some of the potential applications for these new types of glasses?
Imagine metallic glasses that are as strong as steel.
Okay.
But also incredibly flexible.
Wow.
Or imagine ceramic glasses with tailored optical properties.
Okay.
That could revolutionize everything from fiber optics to solar panels.
It's like stepping into a science fiction novel.
I know, right?
We could have glass skyscrapers that bend in the wind.
Right.
Or ultra-efficient solar panels that power entire cities.
Exactly. The potential is there.
Wow.
And it's exciting to think about what the future holds for these amazing materials.
Well, I have to say, I started this deep dive thinking ceramics were all about, pretty pottery and those charming rooster figurines.
Right.
But I'm leaving with a whole new appreciation for the science, the artistry, and the sheer impact these materials have on our world.
It's been a pleasure exploring the world of ceramics with you.
Likewise.
I hope you'll continue to look at these seemingly simple materials with a newfound sense of wonder and curiosity.
I definitely will. Thanks for guiding me through this fascinating deep dive.
You're welcome.
I'm going to look at my coffee mug, my bathroom sink, even my car in a whole new light from now on.
There you go.
And to everyone listening, keep those minds curious and keep exploring.
Yes.
Who knows what hidden wonders you might uncover in the world around you?